So hi all, welcome back to my channel Engineering Chronicles of Plant Design. So today's chronicle or today's video is all about screw conveyor design. So if you are aware, the first screw conveyor was designed by the great mathematician Archimedes. So Archimedes has first invented the screw conveyor in which he used to raise the water from the farmland to the farmland from the river and also from the ships, and in that way the screw conveyor was invented. And the next technological advancement happened in 1898, in which Frank C. Cadwell has patented the first screw conveyor, which is also called as the helicoil flight. So application of screw conveyor, you all may be knowing it. It is used as a transportation device, or we also call it a bulk material handling equipment. It is used to transport material from one end to another. It is also an what we say replacement for a pump where the materials are very sluggish or hard and you may not able to transport it through a pump. So in that case we also use screw conveyor. Okay, it is mainly used for a material which is like a cement or a small quarry, or in a crusher quarry it is used. So there are a lot of application where screw conveyor is used. They also used to transport wheat, rice, in food industry also it is used. Okay, so you may be aware of CEMA. So what is CEMA? CEMA is an association just like ASME. So we have ASME for mechanical equipment design. So same we have CEMA, which is called as Conveyor Equipment Manufacturer Association, which has made some standards and codes to design a screw conveyor. Not only a screw conveyor, it is also in the CEMA standard you can see there is also you can design belt conveyor also. So normally it is a conveyor manufacturer association. So related to conveyor, all the code standards you will find in the CEMA. So before going into the design of the screw conveyor, you should know the parts of the screw conveyor. So this bottom, if you see, this is called conveyor tuff. Here I have mentioned the U type. This can be round type. This can be a trapezium type, depending upon the flow of material which we are getting, which we are flowing through. It is defined. The size is defined. It can also be a box type, the tuff. Okay, this is the, so here we have inlet. So inlet end we will have a bearing, outlet end. So we'll have a motor. So as per good engineering practice, it is also always use the drive at the discharge end to have a good motor efficiency. This is a screw conveyor here in the middle, if you can see. In center, this is a shaft, pipe shaft. Okay, this is a screw, and here we have cut the screw at the end, and here the screw starts and it follows to the end. So for example, if your length of the screw is higher, more than a defined length, so normally we give a hanger bearing. It is nothing but a joint between two screw, and it will be a bearing in between, so the movement is not stopped. And in top we have a tuff cover. In the round, if in the case of a pipe tuff, we don't have tuff cover. So this is a basic uh, typical screw conveyor components which are common in all the almost common in all the type of screw conveyor. We also have shaftless screw conveyor now in the market, in which there will be no shaft. Okay, in the end we'll be having a shaft only, so that we can install bearing here, and we can put a drive in as a drive in a small shaft. But in the middle we will not have any shaft. Okay, but it is restricted to some material, because we may not be able to put a hanger bearing in between, and the length is restricted, and also the material flows is restricted. Okay, so moving ahead to see what is turf loading. So if you see turf loading, we have three pictures in the slides. 15%, in which the material will only be traveling in the 15% of this radial area. Okay, and here if you see 30% of the occupied for transportation, and this is 45% occupied. So depending upon the material flowability and the material application, we define the turf loading for a screw conveyor. So moving ahead, material code and bulk material characteristics. So I have put a table over here. This is from the CEMA standard. If you see, I have taken a small example from CEMA standard. So they have defined, depending upon the material, they have defined the material characteristic. So they have defined based on the bulk density, if it is very fine, granular, lumpy, or irregular. Okay, or if it is based on the flowability, they have defined very free flowing, average flowability, or sluggish, and also based on the abrasiveness. So why abrasiveness? Because if the material is very abrasive, so what will happen is whenever the screw conveyor is moving, the screw flights and the turf will get uh, it will get abrased and the metal thickness will get reduced. So at the end, what will happen? The radial clearance, the clearance between the screw and the turf will go on reducing, and will have a very less conveying at the end. So because of that, we'll define all the thing initially, and based on that, we'll set the material proper, and we'll have a proper clearance. We'll have a proper screw material, tough thickness, screw thickness, all will be defined. Okay. So material characteristic chart. So I have taken again an example from the CEMA standard. Okay, the material characteristic chart. Some material which is given over here, for example, ash playground, ashes, cement, okay, coal, and then dolomite, crushed dolomite, fly ash, gypsum raw, put 1 inch size, limestone crushed, limestone dust. So all this material has in CEMA itself. If you go into a CEMA standard, if you go to if you know someone who have the standard, you can ask them to send. So you can go. They have predefined all the material characteristic inside the table. The initial table, if you start reading the CEMA standard, so the initial table you will find this thing, and based on that they have defined the density of the material and material code they have given, and they have defined component series 1A, 1B, 3D, 2D, okay, and also material factor. This material factor will be using in the design, in the future design. Okay, so let us move ahead. So maximum lump size. So if you see in this picture on the right side, so this is stuff. Okay, conveyor. This is this end to this end we have conveyor diameter, and from the conveyor diameter end to the bottom of the turf, we call it as a clearance. And from the bottom of the turf to the bottom of the shaft, we call it the radial clearance. Okay, so why we go to lump? So lumps are divided into three categories: class 1, class 2, class 3. So class 1 means 10% are lump, ranging from maximum size to one half of the maximum, and 90% are lumps smaller than one half of the maximum. That means there are less lumps provided in the material. And in class 2, 25% are lump, ranging from maximum size to one and a half of the maximum, and 75% are lumps smaller than one half of the maximum size. And in class 3, 95% or more are lumps, ranging from maximum size to one half of the maximum size, and 5% or less are the lumps less than 1/10 of the maximum size. So depending upon the lumps available over here, we'll define the radial clearance. Okay, because what will happen if you don't define the radial clearance? So at the end, your screw flowability of material will be very, it will be problematic. It will have a problematic conveying. So to avoid that, we initially define the lump size of a material, which class the material lumps is, class 1, class 2 or class 3, and based on that we'll provide the radial clearance. So if you see, it is given ratio R 1.75, 2.5, 4.5. So what is R? So R is the ratio between radial clearance, and divide by lump size. What is the lump size? So depending upon the radial clearance, we will select the lump size. Depending on lump size, we'll define the radial clearance, and we'll define the class of the material. Okay. So moving ahead with the screw conveyor capacity formula. So for example, if you want to design a screw conveyor, and you already predefined a size, and in that size, if you want to check what is the material flow capacity depending upon the material, in that case you can apply this formula. This formula, C per rpm, that is flow per rpm, is equal to 0.7854 multiplied by ds square. ds square means diameter of the screw square minus dp square. What is dp? dp is the diameter of the pipe or diameter of the shaft square multiplied by pitch. Pitch, this from here to here, we call it a pitch of the screw. And K is tough loading. For example, 30% will take 0.3, 15% will take 0.15, 45% will take 0.45, and multiply by 60 divided by 16728, we will get capacity in feet per hour. So remember, whenever you are using feet per hour, diameter of the screw and diameter of the pipe will always be in inches, and in fact also the pitch of the screw will be in the inches. So pitch of the screw can also be defined. It can be the same as the diameter of the screw. It can be 0.5 of the 0.5d, or it can be 1.5d also. Long pitch screw also can be there. So this all depend upon the material characteristic, what material you're using. Depending upon that, you can define the pitch of the screw. Okay. So here are some example from the CEMA standard again. They have predefined the diameter of the screw, and they have predefined the capacity of the screw at 1 rpm. As per previous formula, they already predefined here. If you see at the end table, so depending on tough loading, 45%, 30%, 30% A, B category, and 15% category, they have defined the capacity at 1 rpm. We will be using this table in our example ahead. So selection of conveyor speed. So how to select the, for example, now we have found what is the capacity of screw conveyor. Okay, that is per rpm. So how you will define the conveyor speed? So conveyor speed is defined by a formula which is Q into CFO into CF1, CF2, CF3 and C1. So what is Q? Q is the actual flow rate, the required flow rate. For example, whatever material you are required to in your whatever, for example, if you have cement, or if you have barite, you want to have convey it with the capacity of 100 cubic meter per hour. So that will come over here. So CFO is a design factor. So what is, for example, whenever we are designing a conveyor, we always take some percentage of design factor. So we can take from 10-20%. Okay. So limit to 20%. Don't take more than 20%, or else what will happen? Your cost of conveyor will be higher. Okay, so you can limit to a proper, if you have proper design, so limit it to 20%, not more. And in case, always take 110%, that is 1.1 safety factor, to avoid extra additional cost because of the design, over design. Okay, so CFO we said. So C1 is the conveying capacity at 1 rpm, that is depending upon the previous formula which we have seen, or from the table also we can take. And then CF1, CF2, CF3 are the factors depending upon. CF1 is a special conveyor pitch capacity factor. So if your standard pitch, that is I said, if your pitch is equal to diameter of the screw, then CF1 will be 1. If it is 2 by 3rd of the screw, then your CF1 will be 1.5. Half of the screw, then 2. 1 by 1 to the screw diameter, then 0.67. So depending upon these factors, your CF1 will vary. Sorry. And CF2 depending upon the screw flight. If it's a cut flight, if it's a cut and folded flight, ribbon flight, so depending upon the loading, we'll take it from here. Okay. And CF3 is a paddle factor. Normally we take it as 1 only in all the factors. If it is a mixing, if you are mixing something, in that case you have to take it from the reverse pitch angle. Okay. So moving ahead, calculation of the motor power. So as per CEMA, the motor power formula, the main formula is HP. HP means horsepower is equal to HPF plus HPM into F4 divided by efficiency. So HPF formula, again, if we have length multiplied by number of RPM of the screw conveyor designed RPM, and then FD, some factors. We will look into what is FD divided by 10 to the power of 6. Same here, C is the capacity of the flow of the conveyor, length and density, and these factors divided by 10 to the power of 6. So L is the total length of conveyor. Okay, depending upon the length of conveyor, the power will be decided. And then we have hanger bearing factor FB. We have seen the hanger, what is hanger bearing. So and that factor, and then flight factor, conveyor diameter factor, efficiency. So drive efficiency means if your drive is a direct coupled to a shaft, that is gearbox coupled, so that it will have different efficiency. Okay, and material factor we have, if you remember in the first slide which I have, the first table from CEMA which I have shown, all material have a material factor. So based on that also with the power will be divided. So power load factor F0, normally we take F0 always as 1. Okay, you can also take 1.1, 1.2 if you have a overload factor in your company. There's a sometimes you say we need to take 20% overload or 10% overload. In that case, you can take. Otherwise, normally F0 will take as a 1. So why F0 will take 1? Because whenever we size, it will be coming to 6.5 or 7.85, 18.5, and we'll go to a next or above size motor. So in that case, we take F0 as 1. Otherwise, you can also take 1.1, 10% extra or 15% extra depending upon your requirement. Okay. So calculation of motor power if it's an inclined conveyor. So previous formula was for the horizontal straight conveyor. If it's an inclined conveyor, so formula will change. HPH will be, you need to one more will added in the HP, that is HPH, that will be C capacity density into height. How much is the inclination factor? And depending upon that, you'll add it here. So your power will be, the add-on factor will be increased. Okay. So now, as earlier you have seen, hanger bearing factor FB. So depending upon the bearing what you're using, your capacity, your FB rating will be changed, will be given here. And the flight factor, standard flight, cut folded, ribbon flights, and tough, according to tough loading, you can take FF from here. Paddle factor, normally we take as 1, as I said earlier. Then depending upon the screw diameter, there is some factor which is called FD. Okay, so that is the reason why we always say whenever you design a screw, always take the design diameter, screw diameter with the from the predefined category. Don't take 4.5 or 5 inch or 7.5 inch. So this value will not be matching. And your uh, drive which you're using. For example, if you have V belt and sheaves, so it will be 0.94. If you have a gearbox directly coupled, so in case you can take 0.95, 94, 93. Normally, when we design, we take 0.9, and this can also be checked with your gearbox supplier. What is the efficiency of your gearbox supplier? Based on that also, we can change the factor. So now let us quickly go with the sample calculation. How to size a conveyor? Okay, for a cement, Portland cement of capacity 150 tons per hour and distance of conveying is 24 meter. So quickly what we'll do, we'll get information from metal to be conveyed, that is metal characteristic chart. We have cement Portland, we will take the density, we'll take metal code, component series, metal factor 1.4, and this you leave it vertical. Okay. Then moving ahead, step 2, we'll define Q, tons per hour is given, right? So from tons per hour, since we are doing in feet and pound, always when you do calculation, you make sure you predefined your units properly, because if you're using feet, you need to use pound or inches. Don't use kg per hour, don't use grams per hour. And if you not use the units properly, your calculation will be a default, it will not be proper. Okay. So 150 tons per hour will be converted to 68.19 10 to the power of 3 pounds per hour, because from tons kg per hour we have shifted to pounds per hour. Okay, and density we have defined from the previous table, and design factor will take 110%. Okay, so nominal design capacity, what will happen, Qn, that will be Q whatever we have got here divided by density. So we will get, this is because of pound per hour, we convert to feet cube per hour. Since we have had a 10% design factor, so our capacity will change to 797.97, that is nearly equal to 800 feet per hour. So in the future reference, we'll use the capacity as 800 cubic feet per hour. Okay, step 3. So you will design the screw conveyor size. So either you can use this table, as our metal comes in A, metal code A, and you can use, and 30% top loading I am taking. You can use this table, or you can use this formula to define your capacity of the conveyor per RPM. But in my case, what I have done, I have taken example from this table. I'm using 16-inch screw conveyor, and I'm taking at 1 RPM, the capacity is 31.2 cubic feet per hour per RPM. Okay, so I have predefined that here, and based on this, I will use in the further references. To determine the speed of screw conveyor, so what I'll do, N is equal to C by C1. So C, that is 800 cubic feet per hour, divide by C1. C1 we have got 31.2, or from this formula whatever you get, you put here. So you will get a speed, required speed. Okay. There are some safety factors also which we need to take in the speed design, speed calculation, which I have omitted. You can go into that formula, which is N is equal to C by C1 multiplied by CF0, CF1, CF2, CF3. You can take that also, but some we can omit and we can take directly C by C1. Okay. So we got the speed at 25.64 RPM. So now we want to define the equivalent length of screw conveyor. Now 24 meter, right? So 24 meter, what will happen? It will be very huge, very large length. And if you are putting a screw conveyor with 24 meter of length, so you will be have a space design constraint, because you need to put n number of hanger bearing in between. So to avoid that, what I have done here, I have defined 24 meter into 6 meter. Each I have taken 4 different screw conveyor. 1, 2, 3, 4. As you see, this is the inlet, this is the outlet. So outlet of the one conveyor will be inlet of the other conveyor. Okay. If you have space constraint, you put say 24 meter screw conveyor, or else you can do like this. You can do this arrangement. Okay. And as I said, as a good engineering practice, I have used the gearbox, the motor at the discharge end, not at the loading inlet end. Okay, to use the efficiency of the motor properly. So this is how I have defined the screw at 25 meter to 4 different equal lengths, and depending upon that, I have converted 6 meter into feet. It is 19.68 feet. That is nearly equal to 20 feet. Okay, and we have used foot-mounted gearbox coupled to shaft, so our efficiency will be 0.94 or 0.9. Okay, so moving ahead, determine the power of screw conveyor. So to determine the power, we have to find FM, FD, FB, FF, and FP. Okay, so here if you see, we also know the material factor FM, 1.4 from the previous table we have taken for material characteristic chart, and density we have defined 94 pound per cubic feet. Sorry, FD for 16 inch. If you see this table, FD for 16 inch is 106. I've taken 106. So FB, sorry, FB I've taken 1. Since I'm using ball bearing, I can take 1, or here also you can take 4.4 as the maximum hanger bearing factor. 4.4 also you can take, and I've taken 1 here normally. So FF, flight factor, I'm using standard flight because my diameter of the pitch and the diameter of the screw and pitch is same, and 30% loading, so I will take FF as 1. Otherwise you can change depending upon your selection. And FP is equal to 1, that is paddle factor, will normally take 1. And as I said, this 0.94 we will take from the reduction factor of the gearbox, 0.94, for the motor power calculation. So now, since I have taken 20 feet as my equivalent length, so for 20 feet HPF will be 0.05 HP based on this formula. HPM will be 1.504 HP. Okay, and if I couple all this, I'll get the formula. I'll get power as 1.66 HP. So 1.6 HP I'll convert it to kilowatt. It is 1.24 kilowatt. So nearest power rating is 1.5 kilowatt. So for my 6 meter conveyor of 150 tons per hour capacity, the power rating will be 1.5 kilowatt. And I will also design the torque. I will also give a torque rating, that is pound inch, and the moment for the further design. It is for shaft design and all this thing. Okay, so I hope you have enjoyed this video, and I have given a lot of information about the screw design. Maybe we have not covered thickness of the screw flight and tough thickness. Those you can, it is all, it will come into different mechanical design. So now in this video we have already seen the size of the screw, how to size the screw conveyor. I hope you have got knowledge about it, and I hope I have conveyed it properly. So thank you, stay tuned, and please don't forget to like, share, and subscribe my channel. Thank you.